Hi, everybody. Today we are going to talk about hybrid orbital theory. All right. So, in the last lecture, we talked about valence bond theory, right? So, just a recap from last class. According to the valence bond theory, it's like a model to explain bonding in molecules. Atomic orbitals overlap to form bonds. So, for example, if you have to consider hydrogen. So how does bonding in hydrogen happen? So H has one s orbital, right? So two H's combine where the 1s orbitals of both H overlap to form bonds. So now there's one electron each in 1s, right? So two 1s orbitals will combine to form a bond. So we talked about this in last class. Now let's consider diamond and let's think about how we can explain the bonding in diamond. Now, as you can see here, this is the structure of diamond that one can experimentally obtain using something that's called X-ray diffractometry. And we don't need to go into that. But what does this structure tell you? So this structure tells you that each carbon here is bonded to four other carbon atoms, right? And we see that these atoms are situated at equal distances and at equal angles. So this bond angle is same as this bond angle and this bond angle, okay? So each carbon atom is forming four covalent bonds, right? And then the bonded atoms are as far apart from each other as possible. They are pointing towards corners of a tetrahedron, okay? And we'll talk about why it's a tetrahedron later. But now, what evidence shows us, as we just said in the last slide, is each of these bonds is the same length and the bond angle is 109 degrees. So you can consider essentially diamond as a huge molecule which has a network or carbon-carbon bonds. Now, valence bond theory tells us that for each bond that is formed, carbon needs a singly occupied orbital pointing in the direction of that bond, right? So one orbital would combine with one orbital to form one bond. And each carbon is forming how many bonds? Four. Okay, so how is it possible that carbon can form four identical bonds? Let's look at the atomic orbitals that carbon has, right? So for each bond, carbon needs one atomic orbital. So to look at atomic orbitals, what we need is electronic configuration, right? So what's the electron configuration of carbon? Okay, so yes, most people selected A. So the electron configuration of carbon is, since it has 6 electrons, 2 of them are in helium and then 2s2, 2p2. So these 4 electrons are the valence electrons that carbon would use for bonding, right? Now draw an orbital energy diagram for the valence electrons. So we see that when you place these electrons in orbitals, this is how their energy lines up. So we know s orbitals, 2s orbital is lower in energy and it has 2 valence electrons, right? And then there are 3 equal energy 2p orbitals. 2 of them have 1 electron each. Now, do you remember the shapes of these orbitals? Look something like this, right? So they're different. The 2s orbital is spherical, whereas the 3p orbitals are mutually perpendicular. So again, remember in H2, the bond was formed when 1s orbital overlapped with the other 1s orbital. So both those 1s were the same, right? But now we have a problem with carbon here. It has 4 valence electrons, but they are in 2 different type of orbitals. So 2 of them are in 2s and 2 are in 2p. So theoretically, that should give different types of bonds, right? Since the orbitals are different. But all evidence indicates that all 4 bonds are identical. So how can this happen? Clearly, carbon cannot be using its existing atomic orbitals, right, to bond with, or we would get different type of bonds. So here is when the big reveal comes in, hybridization. It uses 4 hybrid orbitals. Now, what are hybrid orbitals? We've not learned about them yet, but now we'll learn about them in the context of carbon. Okay. So before we get into what hybrid orbitals are, I want to tell you that if you combine n atomic orbitals, it'll give you n hybrid orbitals, right? So whatever number of atomic orbitals you combine or mix, it'll give you that same number of hybrid orbitals. Now, how many hybrid orbitals does carbon need? 4, right? Because it's forming 4 bonds. So how many atomic orbitals must combine? 4, also 4, right? And there's a hybridization video here that you can see. But what happens is, now since carbon has to form 4 bonds, it has to use all 4 atomic orbitals. But remember the problem, they're different and they are different in energy. But evidence indicates that it forms 4 identical bonds, right? So what happens is it's going to have to mix them up. So like think of it as putting 2s orbital and 3 2p orbitals together, mixing them up, and you get 4 hybridized orbitals. So you see that I put a spherical 2s orbital and then 3 2p orbitals, which were dumbbell shape, and you get something like this. So these are 4 sp3 orbitals. These are called hybrid orbitals, and now since we combined 1 s orbital and 3 p orbitals, hence we call them sp3, right? So this number indicates however many p orbitals were there. Say we combined 1s and 2p, that would be sp2, and we'll see those cases later on. So we put in 4 atomic orbitals, we got out 4 hybrid orbitals. So just to recap, the atomic orbitals in diamond, basically in carbon, hybridize to form bonding orbitals, right? And these sp3 orbitals are the ones that will form the bond. So individually, they look like these, but then when placed together, they are in tetrahedral geometry. And that is why you see the tetrahedral network of carbon, right? So to form 4 bonds, carbon hybridizes the 4 orbitals, and they're all the same. They're all the same energy, and they naturally assume a tetrahedral geometry. And we'll see in a bit why, but you keep thinking of it. And so how bonding happens is, say this is one carbon, it has 3 sp3 hybridized orbitals, right? And then it combines with another carbon that has similar sp3 orbitals. So they give strong directed bonds. They are called sigma bonds because they happen with end-to-end overlap. So electrons are shared equally between these two. And we can actually use this model of bonding to explain properties of diamond. If diamond were to melt, these bonds would have to be broken, right? But that would need a lot of energy. So this actually explains why diamond is so hard and it actually decomposes rather than melting. All right, this